Good day, ladies and gentlemen. This is still Sahid, bringing you the first lecture in the month of January. I'm sorry this is coming late, and it is due to some logistics that will make the subsequent lectures better than the previous one. We are still on fundamentals. Today we talk about matter, because in this universe there are basically two things: matter and energy, and the study of them make what is called science. So like we have known before, matter is anything that has mass and occupies space. So if we begin to mention the example of matter from now till tomorrow, we will not be able to exhaust it, because factually everything is matter. Even if something does not, I don't even know if there is anything that is no matter, because even here, we may not be able to imagine, it still matter, because anywhere here is, no other thing can be there. So because of that, we are taking our time to study the fundamentals, and we are starting with matters. So at the end of today's class, so it is expected that the students understand matter and the states matter exists, because we are talking about matter, anything that has mass and occupies space. There are some particular states that they are present, and if maybe some properties are changed, there is tendency that some of them will change their particular state and turn to other state. That one does not mean that they cannot turn back to the original state. So after today's class, we'll be able to know what the properties of matter and what is responsible for their state that they are. Again, like we said in the first introductory class, we should be able to differentiate between pure substance, and today I don't want to use impure substance. Let us use mixtures, pure substances and mixtures, because if you say impure substance, it sounds somehow to some people, especially those that are not science oriented. So because of that, let us use mixtures instead of pure substance. So we are differentiating between pure substances and mixtures today, inshallah. And the other part of the lecture will be on measuring matter with metric system and examining the properties of chemical substances. Matter, chemistry is one important branch of science. In the family of science, we have three basic subjects: the physics, biology, and chemistry. And that chemistry is that branch that deal with matter, the composition of matter, their properties, and changes they undergo. That is chemistry. Matter is one of the main components of the universe, the other being energy. As I said before, there are two major things in the universe: the matter and energy. Before, scientists thought that matter and energy are two separate, distinct entities. It was of recent that the concept was understood that, in fact, it is even matter that is being converted into energy. Where can we get that? In the atomic bomb. All of us have heard what atomic bomb is. In nuclear reactor, even in houses, you heat maybe water. When you heat water, you generate steam, It means you have converted matter. Matter is water. Water is an example of matter. You have converted the energy in water into heat energy. So you have converted it into energy. In fact, in some cases, the energy is used to do work, especially in steam turbines, in hydraulic turbines. You can convert matter to energy, and you can use the energy to do work. Everybody is now enjoying electricity, and as we know, electric energy can be generated from various sources, from solar, from anything. So we can generate energy from electricity from various forms of energy. So in fact, steaming the houses, you can generate energy from it. What do you use to steam houses? You can use maybe charcoal. You can use even heater to steam energy. So in that case, matter are converted to energy. There are 3 basic states of matter. We have the solid, the liquid, and the gases. And each of these states has its own peculiar properties that make it possible, that make it responsible for the state to which it belongs, such that if the properties that makes it, let's say, is solid now, the property that makes it is solid, if the property, one of them or some or even all of them now change now, so we can have something like a liquid or a gas in extreme cases. Likewise, in other state like liquid, you can have it in solid, you can have it in gas. Gases can be converted to liquid or solid. What we are trying to say is that each of the 3 states of energy, they are interconvertible. There's no law that says if a substance is in solid state, it must remain in the solid state. No. In fact, what is obtainable is that you can change the state of matter. So we now take each of them one after the other to see what is really responsible for the state to which each of them belongs to. Let's begin with solid. As we all know, there are many solids. There are many examples of solid. Your book, your biro, your pencil, a car, your computer system, your phone, wristwatches, clothes. They are examples of solid substance. Even chalk. And if we look at each of them, we can see that they have definite shape and volume. What are we saying? If you take a biro as an example, all of us can differentiate. If the biro is like hexagon at cross section, but long like a cylinder, so at least someone will be able to define the structure, the shape of it. And the volume, how much is it how big it is? That is what is called volume. So example is ice cube in glass. You can have a glass cup, you put ice in it. If you want to know the volume of ice in it, at least you can know it judging by the volume of the glass cup in which it is occupied. The particles of solid are closely packed and are not moving, but only vibrating because of the tight grip of the individual molecules by the neighboring molecules. What we are trying to say is that if we take chalk as an example now, one should be able to feel the molecules, the compactness that makes it to be in a state to which it is. The particles are close to each other. That is why the shape can form like that. And what makes the particles close together, it is because of the tight grip, the force of attraction that is very strong in between the molecules. Let's say we have A, B, C, D, E, F molecules. So the force of attraction between molecule A and molecule B is very strong. So a molecule A can hold molecule B very tightly, B can hold A, B can hold C, and each of them like that until a very giant structure is formed. And when we have a strong force like that, we don't expect free flow, we don't expect free movement from the molecules. The only thing they can do is to vibrate. The structure is rigid and fine. The structure is rigid, that is why they have that shape. If it is going to be like a ball, a circle, or a oval, if it's going to be rectangular, going to be triangular, it's going to be any shape that is it. It is because of the force of attraction that is between the molecules that makes them to be where they are. And that structure is called crystal lattice. Crystal lattice is just the arrangement of molecules in such irregular repeating pattern. There is no law that says a solid must have a particular shape. It depends on the manufacturer, it depends on the producer of that particular solid. If you like, you can make your own solid a rectangle. Let's say a chalk now. You can make your chalk to be like cylindrical. You can make it like a cone, such that the diameter on top and the diameter at the bottom are not the same. It depends on the manufacturer, the producer, to make the shape the way they are. The most important lesson in this aspect is that solids have definite shape and volume, and it is because of the attraction between the molecules such that free movement are not allowed. So they are confined to where they are. So, the case is not really the same in liquids, although liquids have their own volume, how much they are. You can compare the quantity of let's say water in a small cup and in a 4-liter keg, a jerry can. So the quantity of that liquid in that container determines the volume of the liquid. Liquids have no definite shape because they flow. They just maintain the shape of the container. Example, if you put them in a cube, they form a cube. If you put them in a cylindrical container, they form a cylindrical container. If you put them in a conical container, they form the shape of a cone. They don't have definite shape. What is responsible for it is because of a more distance between the molecules. Unlike in solid that we have a very tightly packed molecules, in liquid the molecules are further apart a bit, and the force of attraction are not as strong as in solid. They move around much more frequently than in solid, hence they don't have particular definite shape. The fact that they don't have definite shape does not make solid superior to them. It is only a property of the present state they are. The last we are talking about on this state of matter is gas. Gases has neither shape nor volume. Gases are even most difficult to deal with out of the 3 states of matter, simply because there is negligible force of attraction in it, though we are coming to that under kinetic theory. The particles are much further apart, hence we can assume that the force of attraction in them is negligible, which makes movement to be very fast, random and haphazard, and independently of each other. So they are able to feel the area that is being contained in them. If you put a gas in a small container, it fill it. The same amount of gas, if you have a large container, they fill it also. That is because the force of attraction in them is very small. So let us now go to change of state. What is called a change of state? Change of state. Each of the three states of matter can be converted to the other. That is what is called a change of state. We can also call it a phase change. So when we get to the thermodynamics of chemistry, so we talk about a change of state and what is responsible for it very well. So a change of state, there are many states, out of the three. If it's solid, change to liquid, liquid change to gas, gas change to liquid. Each of these, they have particular specific scientific name that is being they are being called. We shall take them one after the other now. Let's start with condensation. Condensation is from a word condense. What condenses? If you have a gas, a substance in gaseous state, now suddenly change to a liquid state. That is what is they say a gas condenses. That process is called condensation. The energy of the substance reduces on undergoing condensation. As we have said, in gases, we say the molecules are farther apart simply because they have much more energy, which can make them to move around. So if you now reduce the energy now reduce more, the molecule can come together a bit. As in before they were farther apart, but now they can move together. So if you remove that energy, they can move to a state that they become a solid, a liquid rather, because the force of attraction will have increased more than they were in gases. Another one is freezing. Freeze. If something freezes, it stays as it is. Freezer, something that converts something to solid. They rigid, they stay as they are. So by freezing, the substance changes from liquid to solid. If something changes from liquid to solid, we call it we refer it to it as being frozen. It freezes. It's they grip each other more than before. This is because of forceful reduction of energy between the molecules. We said in the case of condensation that if the energy of the substance reduces, so we can change from a gaseous state to liquid. So if the energy of this liquid state now reduces further, then we can change it to a solid, because the molecules move closer. When they are closer enough, they align themselves, and when they align themselves like that, they form a shape. And what is the state of matter that has a particular shape? Then is solid. That is where we have solid. Solid is just formed from liquid when the energy of the liquid molecules are far reduced, such that they are closer. The force of attraction in them is now very strong, so that they are not free, they are not at liberty to move as they are. They allow themselves to stay aligned closer to each other. That is when we have solid. The temperature at which this occurs is called the freezing point. Freezing. The freezing point is the temperature at which a liquid changes to solid. Each pure substance has its own. For pure water, it takes place at 0. So we can the two processes that have been described above can be represented by this equation. The first one is when a gas changes to liquid. This arrow is removal of heat heat energy from gaseous water, a gaseous, let's say steam, gaseous water, in quote and unquote, gaseous water. If we remove heat energy from it, they will form a liquid. That is called condensation. But freezing is when the energy of the liquid water molecules is reduced further, then they form a solid. Another important change of state is the melting. When a substance melts, it changes from solid to liquid. Substance was in solid before. Heat energy is supplied. If the heat energy is supplied to it, the bond breaks. If the bond breaks, the particles move faster. The particle moves faster, then the substance melts. That is the sequence to which it occurs. Before, the molecules were close to each other. So the heat energy is supplied to heat. What makes them close together before is because of the force of attraction, the strong bond that is holding each of the molecules before. And now the heat energy is now supplied to heat. The effect of the force is now not felt again because the heat energy has been supplied to it, which makes the bond to be weaker. And if the heat energy is continuously supplied to it, the bond now weak to the extent that the particles can move faster and the substance can melt. If the substance melts, it becomes a liquid. The temperature at which this occurs is called the melting point. During the melting point, it is just the assumption, the literary assumption is that, ordinary assumption is that if heat energy is, temperature is increased, heat energy is increased. But in the case of melting, it's not like that. You are supplying the heat does not necessarily mean that temperature is increased. So if a substance is melting, the temperature remains constant throughout the melt. We talk about the freezing point of water to be 0 the other time. The melting point of ice to become water is 0. That is why I wrote notes. The melting point and freezing point are the same for a substance. If we take water as an example now, the melting point of water is 273 Kelvin, which is 0 degrees Celsius. It is the same temperature as freezing point of water, 0 degrees Celsius, because the two processes are reversible. What if water was existing at 10 degrees before, that is a liquid water, you can remove the heat energy in it. When it turns to 0, the water starts freezing. That particular 0 degrees, the temperature will not reduce until all the water molecules has been frozen. During this freezing, the temperature reduces. So when the freezing now completes, then the temperature drops further if the further removal of heat is taking place. The same thing, if you have an ice, let's say at minus 10 degrees now, the heat energy is now being supplied, temperature will increase, minus 10 to minus 9 to minus 1. Then at 0, water starts melting. When it starts melting, even if it is one molecule that starts melting, the temperature remains constant until all the molecules have melted. Then the temperature now increases if the heat energy is continuously being supplied. Boiling takes place in liquid. It cannot take place in solid. So if you have a liquid substance that change from a liquid state to a gaseous state, as a result of constant supply of energy, which makes the molecules to vibrate and the bond holding them is completely broken. So that is when we have a substance changes to gas. The boiling point of is constant for a pure substance, but it is dependent on external atmospheric pressure. The boiling point is constant, but still dependent on atmospheric pressure. What we are trying to say is this: the atmospheric pressure determines the boiling point. Even though the boiling point of water is 100, pure water is 100, that is at standard atmospheric pressure. If there is a way of reducing the atmospheric pressure, let's go we go to the top of a mountain. The atmospheric pressure is lower there, then the water boils before reaching 100. It boils faster in that place than other place than where the atmospheric pressure is 100. So because the boiling point is that point at which the vapor pressure inside the container, the vapor pressure of the water is equal to the external atmospheric pressure. Because as you are heating, the vapor pressure is increasing. If the external atmospheric pressure is 20, the vapor pressure reaches 20 faster than when the external atmospheric pressure is 100. So the external atmospheric pressure determines the boiling point. But the message we are trying to pass here is that the boiling point is the point at which a liquid substance changes to gas, and the boiling itself is when a liquid changes to gas. Because we have to get the two concepts clearly: boiling point and boiling. Boiling is a process. Boiling point is that temperature at which that process takes place. The temperature remains constant through the boiling process, like we have in melting and freezing. Boiling is not an exception. Another concept is sublimation, and this is a bit different from what we are seeing, where we have been discussing before. Because before it was a liquid changes to gas, a gas changes to liquid changes to solid changes to liquid. These are reasonable. But in this case now, a substance changes directly from solid state to gaseous state without passing through the liquid state. Somebody will imagine how is this possible. By the grace of God, before we finish this course, we'll go back to this concept, but not sublimation as a topic, but what is responsible for the solid changing directly to gas shall be examined. Examples of substances that sublime: they are dry ice. Dry ice is a solid form of carbon dioxide. We all know carbon dioxide used to be a gas, but dry ice is when the carbon dioxide is cooled, it becomes a dry ice. There's a process of doing that. Naphthalene, camphor. This is what is used in hair fresheners. You know, hair fresheners, they are usually in solid. When you put them in your room, you'll be smelling the scent of the hair fresheners. But after about maybe 1 or 2 weeks, you will not see anything there. It is because the hair substance the hair freshener that was solid before has been sublimed, and it has been changed to gas through the process that is called sublimation. Ammonium chloride is another example. Mothballs. There are many examples like that. So we are going to another concept called pure substances and mixtures. In the introductory class, we have talked about pure substance and impure substance, but I don't want us to use the word impure substance because it sounds somehow to some laymen that are not, laymen include that are not science inclined. So let us use a more a better word to express what we are trying to express. So because we started from matter. Matter is divided into two: pure substances and mixtures. And pure substances are divided into elements and compounds, like we discussed in the first class. Then the mixtures can be homogeneous or heterogeneous. What makes substance pure? The number one thing is that it consists of pure and definite composition, a constant composition. A constant composition is the first criteria. Number one is the composition does not vary. There is no any condition that is being subjected to that will make the composition vary. So far it is a pure substance. We should not forget that in the first class we said a pure substance is a substance that contains only that substance. If we are taking iron as an example now, iron element as an example, that's to contain only iron. If we are taking water as an example, that's to contain only water. It must not contain anything inside. The example is deionized water. If you have a deionized water, it is a pure substance. But if you're now having water that is mixed with a milk or tea, it is sweet, but the milk there, the tea there, the sugar there it is not making it a pure substance. Although the milk, the sugar, the tea, they are not bad substances, but in this concept we don't need them if we are to define what a pure substance or an impure substance or a mixture is. It is either an element or a compound. So let us start from element now. Elements compose of a single kind of atom. If it is sodium, it is sodium throughout. If it is magnesium, it is magnesium throughout. Then what is an atom? That smallest particle of a substance that can take part in a chemical reaction. That is the definition that we know for atom. So that particular smallest particle has all the properties of the element. What we are trying to say is this. Let us take gold as an example now. If you have a big gold and we try to cut it into small particles, you cut the small to smaller, you cut the smaller to another smaller, smaller to another smaller, to another smaller. A time is coming that you will not be able to cut it further. That particular time that the good remains the good, even though it is small. That smallest particle is called the atom, so that if it is smaller than that, you will not have gold again. That smallest one that still retains that properties of gold is called an atom of gold. The same thing for sodium, same thing for hydrogen, the same thing for iron, for sodium, for calcium, for magnesium, for aluminium, for copper, for molybdenum, for niobium, zirconium, like that. Elements are building blocks of matter. It is these elements that are combined to form matter. If you want a duralumin now, a duralumin is an alloy that contains magnesium, aluminium, copper in various percentages. We are getting to that later in the course by the grace of God. And as an example of matter, like we have said before, matter is a substance that has weight and occupies space. So if you have copper, aluminium, and magnesium put together, you have a duralumin. Like a steel now, iron and carbon. Carbon is an element, iron is an element. You now mix them together. So those are called building blocks. Like you want to build a house, you now have blocks that are put together to erect that house. That house in this case is a matter. The building blocks are the blocks you put together. They are the iron and carbon that you put together to build a house. In this case, the matter, the steel that we are talking about here, that is element. Compounds. We know compound from that word. It's composed of things. So when you have two or more elements in a specific ratio, it's called compound. Don't forget, compound is pure. If you have a pure element, you have another pure element. They now combine together in a specific ratio. Chemically, they are called compound. Example is water. There is no condition that will make the ratio of water to be less than that hydrogen to oxygen of 2:1. Even if the water is present in gaseous form or in solid form, it has to be, the ratio of hydrogen to oxygen has to be 2:1 all the time. There is no condition that make it change. So when you have something like that the ratio is specific all the time, it is called a compound. There are many substances that contain hydrogen and oxygen, but the only one that has the ratio of hydrogen to oxygen is water. So that water is a compound, a pure compound. It is difficult to separate components of compound except in chemical reactions. We are getting to that later. The properties of compound are different from the constituent element. Like you want to form water now. Hydrogen has its own compound properties. Oxygen has its own. If you now combine together to form water, the property of water will not be the same as the property of hydrogen or oxygen. Even it will not be the combination of the property of them. The water will have a property that is different totally from what makes the component, what its constituents, the hydrogen and oxygen in this case. Like in steel, iron and carbon, they are compounds that make up what is called steel. So iron has its own, carbon has its own. If you combine them together to form steel, then the property of steel will not be the same as copper, although this one is more of a mixture. But if we are talking about compound like magnesium sulfate, copper carbonate, magnesium chloride, magnesium has its own, chlorine has its own. When now combined together, they form magnesium chloride, whose properties are not the same as those of the magnesium and chlorine. Mixtures. Mixture is a physical combination of pure substances that give no definite composition. That is the difference between compounds and mixtures. Because we said compound has specific ratio, in the mixture we don't have specific ratio. It depends on the maker, the manufacturer, the producer that is making it. If you have aggregate now, civil engineers, they deal with aggregate very well. Aggregate is the mixture of the sandstone, the fine sand, cement, rocks to build everything combined together to build house. It depends. There is no golden rule. It depends on you. If you want cement to be more than the fine sand, if you want the tight sand to be more than the sandstones, if you want anyone that you want, there is no definite composition that okay you need to get 4 grams of sandstone plus 20 grams of cement. It is not like that. It depends on the maker. Separation is by physical means, e.g. example is filtration. We need to be very careful in the spelling of filtration here. There is no E after T. It is filtration like this. So if you any substance that can be separated by filtration or any other physical means like distillation, they are called mixtures. Like petroleum, like blurs, like the mixture of polymers that makes paint, Other things, they are called mixtures. Example of mixtures, just small example, like sand and salt, sand and water, sweats contain water, salt, and other things according to biologists. So it's a mixture. It can be homogeneous or heterogeneous. What makes it homogeneous? That is when you have a uniform composition such that every portion of that substance is the same throughout. Like we have salt and water mixed together now. If you mix them together, you stir them, anywhere you taste, it tastes exactly the same way as any other part. That is called uniform mixture, homogeneous mixture. That one does not make it pure, but it is called it is homogeneous. These are called solutions. We are getting to solutions later. Heterogeneous, hetero means something that is not constant. Hetero means the opposite of homo. Homo means the same, hetero means different. So when you have different composition such that every part are not the same, they are not the representative of others. In homogeneous, they are representative. If you want to carry out a particular test, or you want to, like cooking soup at home now, or making tea at home, that is just familiar example. Making tea, you put your sugar, your milk, your tea in the water. You don't need to taste the whole of the tea to know if it is sweet or not. You have to take just small portion to know if it is sweet or not. So it is understood, is assumed that it is mixed together, it is homogeneous. So anywhere you take it has the same sweetness as the other part. That is what makes it homogeneous mixture. So heterogeneous is the same. That is when they don't have that property, they don't have that uniqueness, the sameness is not there. Examples are sand and sugar. If you put sand and sugar together, definitely, because sand is heavier than sugar, there is a part that you see more of sand, a part you see more of sugar, a part you see them together but not the same. Mixture of stones of different sizes. All these are practical things that we can see, that we can feel, so as to get the idea of what we are trying to pass here. So we are going to another concept. It is called measurement. Although physicists deals very much more than chemists in measurement, but we just need to talk about it briefly. Measurement is important because it is a single language that every scientist understands. If it is not because of the unified language, the unified way of measuring things, a Russian scientist will speak differently from a French scientist or English scientist or even a Nigerian scientist. But because of the system of unit that is being accepted worldwide, that is why we are able to understand the quantities that we are seeing. So in measurement, we deal with the SI unit, the System International. It is a French, see in italics, System International, SI unit. It's accepted. It's a means of measurement. And what is in SI unit? SI unit is when you have a basic unit that is peculiar to a particular quantity. So if you now want to express the quantity, how much is it, you now add prefix to it. Prefix like kilo. The kilo is small letter K, not capital letter K as some people used to write it. Is small letter. Milli is small letter. It means times 10 raised to the power of minus 3. That is 0.001. Kilo is 10. So all these, they are not peculiar to anything. They are just prefix. I can add it to anything, any quantities, any unit that you want to add. But the units are length in meter, mass in gram, time in seconds, energy in joule, volume in liters, liters in centimeter cube, feet cube, like that. There are other form of volumetric measurement, but here we are talking about liters. So milliliter, that is 0.001 of liter. A liter divided by 1000 is called a milliliter. A joule now, a kilojoule is a joule times 1000. If you have 1 kilojoule, it means 1000 joule. If you have 1 kiloseconds, that is 1000 seconds. A kilogram, 1000 kilogram. 1 milliliter is 1 meter over divided by 1000. That is what we are saying. So there are many measurements that we'll be talking about in this course. So as we are talking about them, we'll be referring to their units appropriately. So properties of substances. These properties enable a substance to change into brand new substance, and also describe how substance react with other substances. That is chemical properties. If you want to know, okay, what's a chemical property of some of particular, let's say sodium hydroxide now, or let's say sodium, potassium, aluminium, water. It means what is the chemical, what if it is subjected to a reaction, what happens to it? That is chemical property. Physical properties, they are something that you can see physically, you can see or you can feel them. Not all the time that you can see them, but you can feel them, like a mass, how heavy something is, like a density, color, is it black, is it white, is it shiny, is it not shiny. So things like that are under physical properties. They don't have anything to do with how substance changes, only the physical features that you can see. And it is divided into two. We have extensive properties and intensive properties. Extensive properties depends on the size of that substance, if it is volume or the weight. Those are called extensive properties. So intensive properties, they don't have anything to do with the shape, the size of that substance. Like boiling point now. A boiling point of 1 liter of water is the boiling point of 1000 liters of water. So boiling point is an intensive physical property. Density, refractive index. This property is important because it makes scientists to identify new substance. Because it is not every time that you can subject a substance, a material, to chemical treatment. I can feel something by its weight. If you have a diamond or a quartz, even though they are of the same color, let us assume that we don't have anything to differentiate them, but we can use their weight. If you hold them you hold the same quantity at hand, you see that diamond is much heavier than quartz. That is density, that is being referred to here as intensive physical properties. It is always the division, the ratio of two extensive properties. Like we have mass and volume. Now if you want to get density, divide it by mass and volume. So if you want to get viscosity, if you want to get refractive index, like that. So there are many examples of extensive and intensive properties, physical properties of a substance, and by the grace of God we shall be treating them in detail later. We will not be able to take questions today, because I want us to finish this concept, the whole of this, before we take questions from jump and as well as assignment. It is hope that after this class our objectives are achieved. If it is so, we'll meet again in the next class.